Today we're going to do a lab on circular motion to find a relationship between two different variables in the circular motion equation. Specifically, what relationship exists between the radius of the path of an object undergoing uniform circular motion and the speed of the object. So what's the relationship between this and between this? The procedure for this is in detail on page 245 and page 246 of your textbook, although I'm going to give you enough detail that you should be able to carry on the lab, carry out the procedure yourself without referring back to your textbook. But if you need to refer to the details in words of the procedure, then go back to page 245 and page 246 of your textbook. We're going to identify three different variables, or three different sets of variables here for this activity: manipulated, responding, and control variables. I'm not going to tell you what they are, but I will give you some hints as we go through the procedure as to what each of these variables are. I'll just remind you right now that there's going to be only one manipulated variable, one responding variable, what changes because of the manipulated variable, and then a number of control variables, thousands of control variables. I don't expect you to list thousands. I expect you to list maybe three-ish. What I want you to do is get the important ones, though. Okay, that's a lot more important to me than the number of control variables that you list whatever's really important. You can list the humidity of the room. Is that a control variable? Yeah, I guess technically it is, but it's not a really important one, right? Okay, there's other ones that are way, way more important. That's what I want to see. Not so much the amount of them, the number that you list, but rather the quality of them that you list. All right, so what's this going to look like? Every group is going to be given a little piece of PVC tubing. This PVC tube is going to be short, maybe about 8 inches long. It's going to be cut at both ends. It's hollow. It's got an opening at both ends. Threaded through the opening at the top and going down through the opening at the bottom is a string. So the string goes in the top and it goes out the bottom. It's not attached in any way to this PVC tube. It's just literally threaded through. It's free to move. If you hold it up vertically, the string's going to fall out. Okay, it's not attached in any way or connected in any way. On one end of the string is going to be a 100-gram mass. On the other end of the string is going to be a rubber stopper. You're going to end up swinging the rubber stopper around in circles. So it's important here that you're careful not to get those two things mixed up. I don't want you swinging a 100-gram steel mass around in a circle in case it happens to fly off. Okay, if you're going to swing something around, it should be the rubber stopper. We don't want anybody to get hit with anything, but if something happens that you do, we'd rather it be a rubber stopper than a 100-gram steel mass. So you've got your rubber stopper, which is attached to your string, which is not attached to but threaded through the PVC tube and attached at the other end to a 100-gram mass. That's basically it. So what are we going to do exactly? Well, you're going to mark off various distances on this string. Let's say we mark off the distance from the rubber stopper to here as 20 centimeters. We want to swing this around at uniform speed, constant speed, such that the rubber stopper maintains a radius of 20 centimeters. That's tricky. It's going to take a little bit of practice to get the hang of that, because what's going to happen initially is you're going to start swinging it, and oh wait, the rubber stopper goes out a little bit further and increases the radius, or the radius decreases depending upon how fast you swing it. You've got to nail it at just the right speed in order to get the radius to be maintained at 20 centimeters. Swing it around, maintain the radius at 20 centimeters. Got it? Then you're going to time how long, once you've got that mastered, you're going to time how long it takes to make 20 revolutions at 20 centimeters. If it changes the radius midstream, you got to start again. If by the time you've got to 19 revolutions, the radius, oops, went too fast and the radius changed, start again. You want to time how long it takes for 20 revolutions at a radius of 20 centimeters, or 0.20 meters. Whatever time that is what it is. Record it. Then do it again for 20 centimeters again. You should theoretically get the same time for time 1 and 2, right? Okay, but the reality is, of course, you're probably going to end up with slightly different times. The closer they are, the better. Then you repeat it. But instead of repeating it for the same radius of 20 centimeters, you, listen carefully, you are going to change the radius to 30 centimeters. You're going to want to have that marked off on the string as well. So now our radius is 0.30 meters. Record the time for 20 revolutions, record the time for 20 revolutions again, and then move the radius to 0.4 meters, to 0.5 meters, to 0.6 meters. Change the value of the radius from 0.2 meters all the way to 0.6 meters in 10 centimeter intervals. Record the time for 20 revolutions in each case. This is your data. This is all I should see for your data. Even though the next table I'm going to show you is quite a bit bigger, it's not data. This is data. Okay, what you're recording as you're actually performing the experiment. This is analysis. Now, the reality is these first three columns are actually just your data table copied over. You don't technically need to include those here with analysis because they need to be included with data separate from the last three columns. But I usually end up including them again under analysis. If you don't, that's okay. But I do need to see these three columns for sure under analysis. The first analysis column, the first column you have to complete a calculation for is the average time. So what we're going to do is say, if this is column A, B, C, D, E, and F, we're going to say the average time is whatever is in column B plus whatever column C is divided by 2. So time 1 plus time 2 divided by 2. The period, the time for one revolution, is going to be whatever in column D divided by 20. Right? It's the average time for 20 revolutions divided by 20 to get the time for one revolution. And the speed is going to be 2 pi r over t, which is 2 times pi times column A divided by the period, which is column E. And then, of course, you're going to repeat that all the way down from 0.2, 0.3, 0.4, 0.5, 0.6 meter radiuses. Once everybody's done collecting data for the lab, I'm going to show you a neat little trick on Google Sheets. It's going to allow you to enter a formula here, enter a formula here, and here, and then literally just copy those formulas down so that you don't need to do all of those calculations by hand with your calculator, unless you choose to. Now, you can see down below, there's a number of analysis questions. The good news is, most of these analysis questions, if you do what you need to do for the tables and so on, you've already got them done. I've circled 2 of them, 5 and 6. The reason I haven't circled number 1, 2, 3, 4, and 7 is because, it's not because you don't need to do them. It's because you just do them already as part of your regular lab write-up. The average time, you've already done that in your table. The period, you've already done that in your table. The speed, 2 pi r over t, you've already done that in your table. The controlled, responding, and manipulated variables, you've already done that earlier on in your lab write-up. Now, you haven't identified the force that's acting as a centripetal force. You haven't determined its value, and you haven't plotted a graph. Should be speed versus radius, by the way, not velocity. Speed versus radius. They're giving you a big hint here too as to what the variables are, right? Remember to plot the manipulated variable on the x-axis and the responding variable on the y-axis. And then number 7, well, we haven't already done that one, but you will when you do your conclusion, right? Because your conclusion is really just, what did you learn? So in your data, I want you to fill in this table. In your analysis, you have to complete this table and answer those 2 questions, 5 and 6, that we won't be answering anywhere else in the lab. Now, for this lab, you're going to actually have to complete a hypothesis. So your conclusion, as you know, if you have a hypothesis, is going to relate back to your hypothesis, which in turn relates back to your problem, right? Your hypothesis should be related to your problem. So if our problem was, what is the relationship between R and V, then your hypothesis would relate R and V to each other. In general, hypothesis should be if the manipulated variable does this, does something, then the responding variable does this. If X goes up, then Y goes up linearly. If P goes up, Q goes down exponentially. Whatever the case may be, right? Whatever you think is going to happen, whatever you think the relationship between radius and speed is going to be. Now remember, your hypothesis doesn't have to be correct. It can be wrong. As long as when you go to write your conclusion, you address that. Your conclusion, when you have a hypothesis, should be in the following form. You want to restate your hypothesis. That doesn't mean you have to state it in different words. You can literally, in fact, you should literally copy out exactly what you wrote back in your hypothesis into your conclusion. If manipulated variable does this, then the responding variable does that. Then I want you to accept or reject your hypothesis. I accept my hypothesis. I reject my hypothesis. Why do you accept or reject your hypothesis? I accept my hypothesis because it's going to come somewhere back into your analysis, right? Always comes back to the analysis. I reject my hypothesis because whatever. If your hypothesis is wrong, that's okay. But you should reflect that in your conclusion. If you find that your hypothesis was wrong, then say, I reject my hypothesis, and this is why I reject my hypothesis. And that's still 100% on a lab, right? Even if your hypothesis is wrong, as long as you realize your hypothesis was wrong. If your hypothesis is wrong and then you go around and go and say, I accept my hypothesis, then that's a problem. What else are we going to have? Sources of error. Okay. Number 2 or 3 good sources of error, plus your suggestions for improvement. What do we got to hand in for this one? Your problem, which I already gave you, so there's nothing there, right? What is the relationship between blah, blah, blah? Your variables, you're manipulated, you're responding, and multiple control variables. Remember to get the important control variables here. Your hypothesis, if manipulated variable does this, then the responding variable does that. Your data, which is the first table that you saw. Notice I'm not making you do the materials. I'm not making you do the procedure here. Your data, which is the table. Your analysis, which is a bigger table and a graph and a couple questions. Your conclusion, which is restate your hypothesis, accept or reject, why, and your sources of error, which are things that could have made it better, or things that could have went wrong, and then suggestions for improvement.